Good morning. I want to show you a technique I found for determining whether or not different variables within data are related to each other in ways that are not obvious necessarily. So I'm going to call this video optimal bias for prediction. What's going to happen is there's like m variables. You could say that this problem originated from me looking at grades of students, and I'm trying to figure out what other scores are the best predictor of the final exam score. And so this has applications, in many places. This might be used for determining whether or not there's hidden relationships within the data. Okay, so we're given a matrix of data, a two-dimensional array of numbers. For the prototypical example is grades of students. So you have rows that correspond to students. There's n rows. And let's say that there are m scores like exam 1, exam 2, exam 3, and homework, quizzes, etc. Which of those variables are related to each other and can be used to predict each other? One thing that I should tell you is that this test I'm going to give only applies for linear relationships that are hidden. Does not apply for nonlinear relationships like exponential or whatnot. So you have a two-dimensional array of numbers. Basically, the first column is going to be taken to be some kind of linear combination of the other m-1 columns. So let me tell you the steps, and then I'll show you some examples. So first, we're going to write the first column as a linear combination of the remaining m-1 columns. Each of those columns is going to get a weight, or we're going to introduce bias. And the other m-1, the coefficients of that linear combination are these alphas. Okay, so these weights are going to be multiplied by the whole column, and then what we're going to do is create a synthetic score with the remaining m-1 columns, and that score will tell us a lot, and the weight will tell us a lot. So the next step is we have a synthetic score, which is the linear combination of the m-1 columns after the first one. And we want to compute the correlation between the first column and the linear combination of the other columns. So our objective function is going to be correlation, and we want to try to maximize correlation subject to the bias we introduce. And I'm going to stipulate that the bias weights, the alphas, are between -1 and 1, which will become a little bit clearer later. So step 4, we see that, okay, so Gij here is the original matrix. Alpha J are the weights, so the sum goes from 2 to m, because we're finding a linear combination of the columns starting with 2 and going up to m. And then AI is going to be this sum here. Okay, so let's get an example going. So here's some stuff, and I know this is in the program called Mathematica. So there's a lot of notation and whatnot. So what I want to show you first is what is it that I have started with here. G is our initial matrix. Okay. Now I suppressed the output. So let me unsuppress the output. This is the initial matrix that we're starting with. Okay. So we have a lot of data, and we're trying to figure out, are these columns related to the other two columns in a linear fashion? So there's about 200 rows of data. So now I'm going to suppress that output and show you, okay, so the objective function is here, and right now it's blue because I have not evaluated this cell yet. It's a function of the bias, the weights we introduced, alpha. Alpha is going to be a length m minus 1 vector, and the objective function is the correlation between the sum that I had written before and the first column of G is here. So it's finding correlation between the linear combination of the other columns, and then the Mathematic has a nice little command for maximizing. Again, it's blue because I have not, in this instance, defined what objective means, but as soon as I evaluate this cell, what it's going to do is, so first is we're taking the coefficient of the first column to be 1. Okay. If we wanted, we could try to do something else like this, where the second column is 1. Basically, we're writing the first column, so it's full value, as a linear combination of alpha 2 times column 2, and then alpha 3 times column 3. And the constraints are here. Without the constraints, we wouldn't get a solution. And that's about how long it takes. What is it telling you? Well, the first bit of information is the 0.06. That tells you that the maximum correlation you'll ever get with these criteria is going to be at most 0.065, and that's a very low correlation. Correlations closer to 0 mean there is no linear relationship present. And how does it achieve that, 0.06? By taking roughly the full value of the second column and 3/4 of the values of the third column. You do that, and you're going to get a correlation of 0.06 at most. Okay, so that's not very much correlation in terms of linear relationships. And let's take a look at the data. Here I'm going to take our initial data matrix, which is G, and I'm going to graph it by using this command here. And there you can see, well, I want to show you how long it takes to actually draw this. So there you go. Takes about 3 seconds to draw a picture. And if you look at this, you can see that there is a lot of noise. Okay, so you wouldn't expect this matrix to represent data that has any interrelationships. When it's noisy like this, there's less likely to be a chance of a linear relationship. Okay, let's go to the next example. So I'm doing a little bit of bookkeeping here to, I want to show you this one as well. There's, sorry. here we go. This matrix. Now, what do you think about that? Are there any hidden relationships between the variables? They're all integers, which doesn't necessarily mean anything. But let's go ahead and do the calculation here. This first row is just how I invented the matrix I just showed you of data. So here, I'm going to run this one. Now it says the maximum correlation coefficient is going to be a 1. That is a strong indicator that there is a relationship hidden between the variables. So that correlation will be maximized when the second bias weight is 0.479, and the third column, we're actually going to subtract roughly 0.234875 of the third column in order to get a perfect or seemingly perfect correlation of 1. Correlation goes between -1 and 1. 0 means basically no correlation. 1 or -1 means that there is a strong linear relationship. So in this data, the way I made it, the columns are I, 2I, and 4I. And don't worry about these times 0.1 point. That's how Mathematica works, to tell it to approximate the objective function. If I didn't have these times ones, I guess they don't all need points, but if you did, you would get that. If I remove this 1 point, it will use exact values, and the objective function will look very nasty. So we saw that in this matrix of data here, the maximum correlation possible is 1, and that's great. So it tells you that the first column is roughly half the second column, and then minus about a quarter of the third column, roughly speaking. Let's do another example. Oh, this one, when I show you a picture of it, it is pretty boring, really smooth, okay? And when it's smooth like that and not noisy, that means that there probably is a linear relationship between the variables, which are the columns. Again, this table, now I'm going to up the ante, well, sort of, and go to 200 rows. Remember, the rows corresponds to students in the main example of what this is for. So now we have a table that looks like this. Let me show you what this matrix looks like. So now we have 4 columns. Okay, and this is part of the matrix. We can see that the first column is very predictable. The second column is double the first column. The third column is also related to the first column. And the last column, we're not sure. It's increasing at a steady rate, so it might be related to the first column. Let's run this through the engine and see what happens. So this table here, all that did was that generated some data for us. Now we have 4 columns, so I'm upping the alpha length to alpha 2, alpha 3, alpha 4, and then I add some constraints for alpha. Let's solve this. Let's just show you how long it takes. There, so that had 200 rows and 4 columns, which is not that much. One thing I'm concerned about is how long it'll take this thing to run if I goes up to something in the millions, or the number of columns is large. That increases the difficulty of the optimization. So here is a set of weights which corresponds to how the correlation would be maximized to 1. So since the correlation is potentially 1, if you weigh the other columns this way, let's look at the data and see if it's noisy or not. So we get not. And once again, the correlation is 1, and we got some rather boring looking stuff. If it's smooth and boring, then what that probably means is that there is a linear relationship. Now, let's start introducing noise and see if we can break this technique. So once again, we have 4 columns, but now the 4th column is going to be a random number between -100 and 100. So if I'm going to show you what this one looks like. Okay, so there. Yeah. Okay, so we have the first column is definitely related to the second and third columns. The 4th column, however, has a lot of noise. Okay, see the noise? There isn't much of a pattern, it seems. So let's see what happens in the method. Okay, so we got a correlation of 1 again here. So that might suggest that the technique is broken, but it's not, because look what happens. The weight of the 4th column is this number, and 10 to the minus 8, as you probably know, is a very small number. In fact, this alpha 4 is very close to 0. So in order, what this method detected here, this is probably the most interesting example so far. The maximum correlation attainable is 1, and the non-negligible weights have these 2 values. And then it detected a bunch of noise in the 4th column. So it says basically multiply that column by 0, and then you will get your maximum correlation. So it detects noisy columns, if you will. Let's keep going. So here's another one. Here's one where the correlation, let me show you what that data looks like. Noise. We get some noise again. Notice how there's some noise and some smoothness. So it's kind of like a border between boring and not boring. And yeah, we get the best noise profile by looking here. Okay, so it tells us that the correlation can be 1 as long as we effectively suppress the 4th column. So let's try another one. Now the 1st column is going to be noisy, and the 4th column is noisy. Now it says that the maximum correlation is 0.07, attained with these 3 weights or biases. And that means there isn't really a relationship between the 1st column, which is noise, and the other 3 columns. The other 3 columns, the first 2 are not noisy, and then the 4th column is noisy. So the noise present here leads to a lack of a very high correlation maximum. 0.07 is a very low correlation, basically none. So notice that it says that, at least in absolute value, the 2nd alpha is roughly double the 3rd alpha in absolute value. And that makes sense because the 2nd column is roughly half of the 1st column. And now alpha 4 is -0.56. So it's not suppressing, it's not telling us anything close to 0, but that's because the correlation maximum, this is the maximum correlation, is only 0.07. So when this number is low, the correlation maximum is low, that suggests not very much of a linear relationship. Okay, let's do another example. So now all the columns are noisy. Okay, all the columns involve random numbers. Here's 4 columns again and 200 rows. So again, remember there's noise here because of the random numbers, okay, that we're generating. Here the maximum correlation is 0.035, which is basically almost perfectly no relationship that's linear. And here are the weights it gives. Let's draw that one. Very noisy. Okay, so we don't expect any correlation, and we didn't get any. Remember, the correlation we're finding, we're actually finding them. We're basically saying what combination of the other columns gives us the best correlation. And here, the best correlation you can get is 0.03. Let's try another one. Now we're having a bunch of random numbers all close to 0. Just take my word for it on that. These random numbers are all going to be very close to 0. So let's see if that makes them more correlated or not. And once again, we have a very low maximum correlation attained for these weights. Notice that A3 is getting close to 0 at 0.005. So it basically means there's no relationship if this correlation is close to 0. Let's graph that one. Just noise. Okay, remember boring means there is a correlation that's there. So close to 1 correlation, and then noise like this will have correlation close to 0. Now I'm going to tackle the case of some nonlinear relations between the columns. Here the first column is going to be the square root of the row number. The second column is the cube root of the row number, and so on. These are all nonlinear functions of the row number. So let's see what happens. So now we have a correlation of 1. When there's a correlation of 1, that means there is a linear relationship between the columns, and that is attained by a close to 0 alpha 2, which basically is almost like suppressing that. A3, alpha 3, and alpha 4 would be given here to attain that maximum correlation of 1. So even though the correlation even though the relationships are nonlinear, it detected a correlation of 1 possible. Okay, so that's basically it. I want to know if this method has a name and what it's called, and if you can help, leave a comment. Thanks.